So today what I'd like to start with is telling you about the complexity classes EXP and NEXP with a focus on EXP, and just so that we'll see how this relates to P versus NP. So note that right now sort of the leading questions are P versus NP and NP versus co-NP. We will come up with more such complexity questions along the way, and some part of it is really inspired by trying to figure out whether there are other methods of approaching or attacking this problem. So let's look at our first complexity class, which is
Ash, I don't think you're sharing screen yet.
Oh, oops. Sorry. Yes, that would be a problem. That would be a problem. There. Do you see it now?
Yep.
Okay.
And also a reminder to begin recording if you haven't already.
So that I started.
Okay.
But I forgot to share screen. So yes, EXP and NEXP, exponential time and non-deterministic exponential time. I said with the leading questions P versus NP and P versus co-NP. So let me define what exponential time is. This is the union of c greater than 1 of d time 2 to the n to the c. Right? This is exponential time, and non-deterministic exponential time is basically non-deterministic time 2 to the n to the c. So these are, if you think about it, these are extremely large or powerful classes, right? Exponential time algorithms. And it's not just 2 to the O of n, but 2 to the n to the c, and non-deterministic exponential time. This seems like huge classes, like very far away from what we're studying. Typically, most combinatorial optimization problems will be, sort of in P, NP, and we'll see P space. But there are situations where you get, questions of exponential and non-deterministic exponential time in database theory, or in various questions about languages. Like if you have two regular expressions and you want to know if they're the same language, and questions of this form often end up being in these classes. So first is it's a relatively simple claim that NP is an EXP, and I won't write out the full proof. I might, as an exercise, but it should be fairly easy to guess that the proof idea is simply for L in NP, we have an exponential time algorithm that simply tries all certificates. Right? And this would give an exponential time algorithm. Or you can think of it as simulate all non-deterministic paths. Okay, so therefore NP is an EXP. So here's a theorem that is not so trivial, and it's what it says is if EXP is not equal to NEXP, so if exponential time is not non-deterministic exponential time, then P is not equal to NP. So again, one of the reasons you could think to define this is just to try to understand the relationships between, so it's sort of trying to understand what is the power of non-determinism. And this is saying that if non-determinism actually has power in exponential time, then it will also have power in polynomial time. Power meaning that it can actually do something that you cannot do in polynomial time. And the proof of this, while it's fairly short, it's a very, very common argument in complexity theory, and it's called a padding argument. So let me just zoom out a bit. Okay, so it's a padding argument. So what is a padding argument? So a padding argument is a way of taking a function in a large time complexity class like EXP and converting it into a language in a much smaller time complexity class, basically by padding the input. Okay, so let me give you the argument. And as these theorems go, they typically will go by the contrapositive. So let's assume P is equal to NP. And we will prove that exp is equal to NEXP. Okay, so we're going to prove the contrapositive. And so the way this works is, we'll say, okay, so consider some language L in non-deterministic exponential time. Okay, so let's think of it in terms of a non-deterministic Turing machine. So that means that basically L is in non-deterministic time 2 to the n to the c. So there exists some c greater than 1 such that L is in non-deterministic time 2 to the n to the c. So there is a non-deterministic Turing machine M that runs in 2 to the n to the c time. We can say O of 2 to the n to the c time and decides L. Okay? Now what I'm going to argue, I'm going to come up with another language. I'm going to call this L pad. So this is a padded version of L. So now I'm going to encode the language is basically going to be all strings where you have X, and then I pad the input with enough ones, 2 to the X to the C. I hope you can read that. So it's 2 to the X to the C, where X is in L. So think of it as basically you take X and then you just pad it with lots of ones. And the length of this is going to be 2 to the X to the C. Now, what can you say about L pad? What can you say about L pad? Can you use the non-deterministic machine M to decide L pad? Imagine the non-deterministic Turing machine M that on some input first checks if it's of this form. Some string and then a bunch of ones of that size. So it can go ahead and check this. Can do this in time linear in the input. And if it is, then it basically removes all the ones and just runs on X as before. Okay? What is the running time of that procedure? Okay, so I'm going to write this down now. I want you to think about that. So I'm going to define a new machine now, and that machine is going to decide LPAD. So let us design a non-deterministic Turing machine M prime that decides LPAD. Okay? So I'm just going to leave the definition of LPAD over here. Okay. And just to make a distinction, I'm going to call the inputs to M prime Y as opposed to X, just so that you can you can see the distinction. So I'll say M prime on input, maybe I'll call it W. W is the input to M prime. Checks if W is an encoding of some string and 1 to the 2 to the X to the C. Right? So it just has to check whether it's some string, and then at some point is everything else 1 exactly of this length. And no, so if not, just reject. Okay, so suppose it is, then it runs M. Remember, M is the Turing machine that decides L. Run M on X and simply follow the output. Meaning that if this accepts, then accept, otherwise reject. Okay, so this is my machine. So the question is, what is the running time of M? Okay, that's the question. So I'm just going to poll you. Hang on. Okay. So the question is, what is the running time of this machine? And so this requires a simulation, right? So you have to simulate. Well, actually, no, sorry, my apologies. Ignore that. Ignore my comment. There is no simulation. So you simply have an no, forget about that. You have an algorithm. You just run it on X. So my question is, what is the running time? Is it O of n? Is it poly n? Or is it 2 to the n to the c? O of that. Again, give me the best answer.
So the input to the Turing machine is X and all the ones, right?
Yes, it's W.
Yes, right.
It's W.
Gotcha. What is the running time of M to begin with?
Of M. The running time of M is O of 2 to the n to the c.
Okay.
Okay? All right, so it's essentially one of these. The thing is, it's polynomial. You can see it's polynomial, although I actually think it's linear, so I hope I haven't made a mistake. but it's definitely polynomial in n. Why? What is n? N is the size of w, which is exponentially larger than x. I believe that this step can be done in O of n time, because it basically has to scan, look at how many ones there are, and then it has to basically compute. It has to. There has to be some equations that it needs to solve, because it has to find out which one. But clearly, you could easily do it in O of n squared. Right? Basically, you could just go everywhere over here, go to each position, just check if all of those are ones, and then check that the length of that is equal to this. So maybe O of n squared, I should be careful. Definitely I can do it in O of n squared. And if I'm more careful, probably in linear time. The running time of the second step is simply O of n, because the running time of this part is 2 to the x to the 2 to the size of the x to the c, but that's part of the input. So this machine drops that input. And so it's definitely polynomial. So I think I should have checked more carefully whether it's n or n squared, but clearly it's polynomial in n. So my apologies for doing a bait and switch over there. But those of you who said poly n, you're absolutely right. It's polynomial in n. Right? And so what that gives us, what does that tell us now? So L pad is in which class? What class is it now? What complexity class?
It's in P, right? Oh, you mean in terms of X and X?
Tell me, what is the best class that you can put it in? What is L pad in? I gave you a machine. The machine runs in polynomial time.
It's a P.
But what about this simulation? It has to run m on x.
Oh, true. But
it's not a simulation.
But the input size is in terms of the input size, right?
You're absolutely right. It runs in polynomial time, but what kind of a Turing machine is it?
Non-deterministic?
It's a non-deterministic Turing machine, right? Because it's running
Oh, right.
So this is actually an NP.
Right. Of course.
Right, it's an NP. But we assumed P is equal to NP. Therefore, LPAD is in P. Of course, it's in P not because of this M prime, it's because of the assumption. So the padded language is in P.
Where is the non-determinism in M prime?
In running M on X. M is a non-deterministic Turing machine by assumption.
Okay.
Because we started by the assumption that L is a NEXP. So maybe I should be more clearer here, right? I want to show that if P is equal to NP, then EXP is equal to NEXP. So I'm going to take a language in NEXP and show that it's an EXP. So I'm going to start with the non-deterministic Turing machine that decides L. I'm going to pad the input so that in effect it becomes polynomial time. And now P is equal to NP. So the padded language is actually an exponential time. So I have an exponential time algorithm. And now basically I'm going to come up with, my apologies, I said LPAD is in polynomial time. And I'm going to use this to come up with an exponential time algorithm for L. Which, as you'll see, is, you may be able to guess how you'll do that. So if LPAD is in P, let us show that L is an EXP. How? Any thoughts? just to show you what LPAD is again. So remember, LPAD is the encoding of x, 1, 2 to the x to the c, right? Just padded the input for all x in L.
Well, since LPAD is in P, we know there's an algorithm that can solve this in P time, and then we just get rid of the parsing of the ones, I guess, and then we would have something for X directly.
For L, you want something for L. You have a machine for LPADs. Okay, let me write this down, right? So there exists a polynomial time Turing machine, and let me call that N, that decides.
Oh, you just pad it and then send it into LPAD.
Exactly, you just pad it and send it to LPAD, right? So, right? So you basically take your input, you pad it with exponentially many ones, and then you feed it to LPAD. So now consider N prime on input W. What does it do? It basically constructs W, or maybe I'll say X, call this X. It constructs X, 1, 2 to the X to the C. And, feeds this to N and follows the output. Right? So N runs in basically in exponential time, right? Because it's going to run in something polynomial in the input size. So it's going to run something in polynomial in 2 to the N to the C time. So L is an EXP. So what does that mean? It means that P equal to NP implies EXP is equal to NEXP. And that's the end of the proof. The contrapositive would say if you prove EXP is not equal to NEXP, then P is not equal to NP. Does this argument make sense? It's pretty clever, but a padding argument is very common. And even if you think about how we constructed like this canonical NP language, it was by padding, right? You basically pad with sort of the runtime. And by a lot of clever padding arguments, you can prove things like this. Any questions about that?
I had a question from the beginning.
Yes.
If I can ask. Why is the class EXP defined as such? Like when I think of exponential, I think of like C to the N and different C's. Why is it defined in this specific way?
Good question. So why do you do 2 to the N to the C and not just, essentially what you're saying is do 2 to the O of C? Like 2 to the C times N.
Yeah, something like that.
Essentially, if you did that, so that class is actually referred to as, I believe it's referred to as E, which is the union of C greater than 1, D time 2 to the Cn. This inequality is not going to hold anymore, so obviously, because if you think about the certificate size is polynomial. So the certificate size is n to the c. So all possible certificates is 2 to the n to the c, not 2 to the cn. Does that make sense?
I see. That's why the polynomials.
So you want to exponentiate all polynomials, not just exponentiate the linear polynomial.
Right, that makes sense.
So okay. This is, but this class also does appear in complexity theory. So it's a completely valid question as to why not look at E.
Well, also, isn't X like closed under like raising it to a polynomial?
So this satisfies a lot of closure properties.
Mm-hmm.
Which you would not get over here.
Right.
So it's this is somewhat nicer. Also, what happens is, because we think of polynomial time reductions sort of as efficient, like suppose you had an exponential time algorithm but you applied it after doing a polynomial time reduction, then the problem is that the reduction could blow up the input by a polynomial. So if you want to have nice notions of reductions as well, then you need to have 2 to the n to the c. Does that make sense?
That
Because
makes
when
sense.
you go from L to L prime, you start at some input x, and let's say your mapping reduction is f, then the size of f of x is polynomial in x. So if you ran an exponential time algorithm on f of x, then you would get 2 to the n to the c, like even if you had 2 to the c n runtime. So you wouldn't have these nice closure properties under doing reductions.
Right. Okay.
So you would only have to look at you would only have to look at reductions that only blow up by linear, and then this would be closed. And this is actually an ongoing topic, new topic in complexity called fine-grained complexity, where you actually look at reductions that only blow up linear because they have certain special properties, like this sort of closure. But if you think of polynomial time reductions, or you think of efficient reductions, or those that run in polynomial time, then you're kind of forced to take exp to be of that form.
Gotcha. That makes more sense in terms of the intuition behind this.
The intuition behind this, and of course, then I guess my first answer was probably not the best one, which is that's to give you this. I mean, I think the correct answer is really that when you look at reductions of this form, efficient reductions, it's exp that is going to be closed under like taking reductions and applying an exp algorithm, whereas E is not going to have that property.
Yeah, for a long time I was confused, like why is NP in E? Because I thought the E was like this E, not the X.
Right. Yes.
So now it makes sense why NP is an X.
Yes. Yeah. Any other questions?
Another question from the theorem: is the converse true or is the proof false?
The converse, that's a good question. That if P is not equal to NP, then is exp not equal to NEXP? And that's, I mean, I don't think it's going to be false, if anything, because the belief is that all of these classes are different. So the belief would be it's true. But I think that, I don't think, I mean, as far as I know, I don't think there's any proof. It seems unlikely that you could get something so direct, because what this is saying is, if P is different from NP, exp and NEXP could be completely different beasts, sort of in one direction. On the other hand, if P is equal to NP, then sort of the padding gives you things.
Gotcha.
But
is there like a reverse padding kind of procedure or something that's out there?
But then you only get, you're only getting lower bounds, right? You're saying if P is not equal to NP, then exp is not. So then what you want to say is that if exp is equal to NEXP, then P is equal to NP.
Oh yeah, that is a big claim.
So then you want to say that what you're basically saying is you're saying that if exp is equal to NEXP, then P is equal to NP. And that is not entirely it's not entirely clear why that should be the case. Right? Because you could have a lot of structure within exponential time which doesn't hold outside, and the structure within allows maybe P what could happen is maybe within X P is not equal to N, because maybe the picture is you have P and then you have NP here, and then you have exp over here, and then you have NEXP sort of over here. And so the converse of this would say if exp is equal to NEXP, then P is equal to NP. So that if these two things are the same, then these two things have to be the same. And what seems with these padding arguments is actually that just because these are the same doesn't say anything about the structure within here. But if P is equal to NP, then that says something about things outside.
Gotcha. Okay.
Any other questions?
I guess I would like to make sure I understand this completely. So just to reiterate,
Sure.
So we're assuming P equals NP, and we're trying to say that next that any that next is within X, right? But
Yes, NEXP is equal to
equal.
EXP because
Equal to X.
NEXP trivially contains EXP.
Yes.
So you just need to show Go on.
So from there, so we take a Turing machine, we take a language in NEXP, and then it has a Turing machine that decides it in exponential time with that NTM, right?
Yeah, non-deterministic exponential time.
Yes.
Yes.
So then we pad it to form a new language that can be decided in NP.
Yes.
But because P equals NP, then it decides it in P, and from there, we can take the original X, and then we can make a Turing machine that can solve it, that can decide it in X, because it just does the padding operation and then passes it to the
Exactly.
Turing machine.
Precisely. That's exactly the
Gotcha.
argument.
Perfect. All right.
And so this is sort of a common argument used to sort of go, in some sense, you go down the hierarchy. Like, if you have equalities lower in the hierarchy, you get equalities higher in the hierarchy by this procedure. Because
Gotcha.
in some sense, what you can do is by padding, you can always, in effect, reduce the running time. You can convert an exponential time machine into a polynomial time machine just by padding the input. That's sort of the argument. Okay. So the next statement that I want to discuss with regards to EXP is actually a very powerful statement called the time hierarchy theorem. And I say powerful because complexity theory is absolutely littered with examples where we just don't know. Is P NP? We don't know. Is P space P not equal to P space? We don't know. Is L not equal to P? We don't know. There's just so many inequalities, but there are some things, very few of them, that we can actually show, and the time hierarchy theorem is one of them. So the time hierarchy theorem says, let Fg be time constructible. Again, this is a technical condition just saying that f of n can actually be computed, by a Turing machine. It's only ignore it. If it bothers you, just think of f and g as well-behaved functions, polynomials, exponentials, logarithmic, the standard kind of functions, such that fn log fn divided by gn goes to 0 as n goes to infinity. This is in effect basically just saying that fn log fn is little o of gn. And if this is sort of confusing you what this condition means, we'll come back to it. Just think of it as fn is smaller than g of n. Right? That's what you want to think of. Fn is smaller than g of n. Then d time f of n is a strict subset of d time g of n. So you get a strict subset. So what you're saying is, if in effect it's like, think of like p not equal to np. This is saying d time fn is not d time g of n. So when you increase the running time, you actually can compute more. There are certain languages that can be decided in g of n but not decided in f of n, where f of n is essentially little o of g of n, but a little bit smaller. You need this extra log n, and this is going to come from the simulation argument. Does the theorem make sense? So please ask me questions if the theorem statement doesn't make sense. Okay? The proof is actually diagonalization. Now it's a clever diagonalization. Okay, so here's what's, let me explain what this is. I'm just going to use some notation. So for any string x, well, actually, I don't think this is even necessary. Okay, so I'm going to actually construct a machine right now. So construct a machine M. So M, and as we do our standard diagonalization, it is going to assume that its input is actually a Turing machine. It's just going to assume its input is code. It is going to simulate n on this using, let's say, the efficient simulation of Henny and Stearns. Again, if you've forgotten what Henny and Stearns is, don't worry, I'll explain it to you again. It's just, think of it as the universal Turing machine, using the universal Turing machine of Henny. It's just going to simulate its input, which it interprets as a Turing machine, on itself. And the key is for g of n steps. Remember, n is basically the size of the input. Okay, n is going to be the size of the input. So it's going to simulate this Turing machine for that many steps. And if the simulation halts, just flip the output. Flip the output, else just reject. Okay, so it's a very analogous to diagonalization style proofs. What it's going to do, what this Turing machine M is going to do, is it's going to simulate its input. It's going to take its input, which it interprets as a Turing machine, simulate that on itself, on n. So it takes n as the input and just simulates it on that string using an efficient simulation. And it's going to run this for g of n steps. Remember, g of n is our larger function. G of n is the larger function. And if the simulation halts, it's going to flip the output. And if the simulation did not halt on g of n steps, it's just going to reject. Okay? Now, what should be apparent here is that L of m, the language accepted by this Turing machine, is in d time g of n by construction. Okay? By construction. So any questions about what this machine is doing? Any questions about what this machine is doing? Okay. Now we will show that L of m is not in d time f of n. And we'll basically use diagonalization style argument. We'll say that suppose it was in d time fn, then it's going to be, there's going to be some Turing machine which can decide this language in f of n time, and then we're just going to feed that into this and we'll get a contradiction. Okay? So suppose not. So suppose, okay, so this is what we're going to show. Suppose, for contradiction's sake, that this language was actually in d time fn. Okay? Decided by a Turing machine m prime. So there's some m prime that runs in f of n time. Okay, so now let's go and look at the properties of m prime. So m prime on input x halts in f of x time, for all x. Sort of for all inputs x, it's going to have this property. Now, what we're going to do is we want to feed m prime to this. I want to feed m prime to this and try to get a contradiction. Okay? And what we're going to say is that because m prime runs in f of n time, and f of n log n is much smaller than gn, the simulation will always halt. And if the simulation always halts, then it's going to flip the output, and we're going to get a contradiction from here. All right, so this is, let's walk through this a little carefully. So m prime on input x halts in f of x time. Now consider some m double prime, and we're going to see this is like a technicality, and we'll walk through this. Consider some m double prime. It's another machine that is equivalent to m prime, but has a large enough encoding length to ensure that f of the encoding length of m prime log of the encoding length of m double prime is less than g of the encoding length of m double prime. So I'm just essentially I'm going to pad the description with empty states or extra states that will never be reached. If you want to think of code, I'm just going to add comments to the code. I'm going to add lots of comments just to ensure that the length of the code is sufficiently long. Okay, that the length of the code is sufficiently long. So let's get something straight here, right? So that m is equivalent to m prime, right? Because they're deciding the same, by equivalent I mean they decide the same languages, right? Because L of m is equal to L of m prime. M runs in g of n. This runs in f of n, which is much more efficient. And m prime is equivalent to m double prime. By equivalent, I mean that the languages are the same. This is just saying that L m double prime is equal to L m prime, which is also equal to Lm. So all of these machines essentially just have the same behavior. So okay, so maybe I I misspoke over here. So I shouldn't say this is equivalent. So this is not true. I say you have this property. It's not equivalent. Because equivalent means that the same running time. The behavior is identical. So my apologies. These are not equivalent. You have two machines, M and M prime. We started with M. That was the machine that we defined over here. This machine runs in G of n steps. We said from the contradiction, we got another machine which accepts the same language that runs in F of n. The languages are the same. Then we construct another Turing machine that is equivalent, meaning that it's just the same machine, except its encoding length is much larger, just by padding with extra states and transitions that will never happen, or adding comments. All right? Okay, so any questions about where we are? Okay, so now let us run M on the encoding of M double prime and see what happens. Okay, remember this is M. Just going to sort of move this in here. Okay. Right, so we're going to simulate. So this is going to simulate M double prime on itself for these many steps. First question, will the simulation halt? Will the simulation halt?
So, M double prime runs in f of n, log f of n, log n f of n steps, right?
So, okay, so I should be clear. So maybe this is something I didn't say. So the Henny and Stearns basically does a simulation with an extra log factor, if you recall.
Right, okay.
Right? So, okay, so let's break this down here. So M prime on itself runs in F of M prime time. Right?
Right, right.
The simulation by Henny and Stearns runs in F of M prime log of that. I just want to write the same thing again, right?
Sure.
And this is less than G of, I'm just going to call this n now, because this is the input size, right? This is n. The input length is n.
Mm-hmm.
So this runs in less than G of n. So
Gotcha.
The simulation will halt. Right? So what this means is that the output of M on M double prime is the opposite of M double prime on M double prime. But that's a contradiction, because we said that the languages have to be the same. So that's a contradiction. So Lm is not in d time f of n. Okay, so this is this is a bit to take in. This is quite a bit to take in. So let's go over this again. What's the idea? Let's go back to this machine. You want to say that d time fn is not d time gn, meaning that there is a language that runs in g of n time, there is a language that can be decided in g of n that cannot be decided in f of n. And so you construct this by diagonalization. You say that g of n is enough time for me to simulate any f of n time run Turing machine. G of n is, that's why g of n has to be larger than fn log n, because g of n time is enough to simulate any machine that runs in f of n. So in g of n time, I could basically simulate any f of n machine and flip the output. This machine that I have constructed cannot run in f of n time because it would be flipping its own output. Or this machine cannot be decided by some other machine that runs in f of n time because it could flip its own output. Okay, so let's walk through this again. So we say construct a machine that basically simulates its input on itself in g of n for g of n steps. That's what this is doing, right? It simply takes its input, simulates it on itself for g of n steps. So it runs in g of n. Whatever this accepts is definitely a language. That's a language in d time g of n by construction. Now suppose whatever language we constructed here could actually be simulated much faster. So there would be some other Turing machine that can simulate, or I'm sorry, not simulate. Suppose there was another Turing machine that decided L of m much faster. So there is this other machine that runs in d time f of n, which is much, so it's a much faster machine for whatever language this accepts. Now you take that machine and you simply feed it in here. The simulation is going to terminate because g of n is enough to simulate an fn time Turing machine. G of n is enough to simulate an fn time Turing machine. Don't worry about the m double prime now. So this is like m prime. So g of n is enough to simulate the fn time Turing machine. And therefore what this machine would be doing was flipping the output. And that gives you the contradiction. Because the machine that was input accepts the same language as m. This is really clever, right? So the machine that was input has the same language as m. That means that the simulation should not be able to terminate. That simulation should not terminate in so many steps. Which means that any machine that has the same language as m has to run for so long that the simulation will actually not halt. That is, it won't stop. Because otherwise it could flip the output. Okay? Now the only reason for the m double prime, and now in hindsight I realize that I should have actually said that if instead of the limit, if you simply said, if you took a function such that for all n, fn log n is less than gn, then that's all you need. Then you don't need the m double prime. You only need the m double prime because technically for small values of n, maybe this inequality does not hold. Maybe the function is not smaller because of some, this is like a big O type thing. And so even in the limit, as long as g of n is larger, significantly larger, you can essentially pad the description to ensure this happens. Does that make sense? So please ask me questions. This is not the, it's a little tricky, the proof.
So the language that m accepts is if n, okay, so if n runs in less time than m, then the language that m accepts is everything that n rejects, right?
Exactly. It's like it's flipping the language.
Right. So if we pass in to m the same language that m accepts, then there's no way that, because if you flip it, they'll never agree.
Right.
Right. And so the only way to make them agree would be to run it for more than g of n steps.
Essentially, the simulation should not halt then in so much time.
Right. It can, because if it halts in less than g of n steps, then it'll never be right.
Exactly.
So it can't do that.
Yeah. So that means that for any machine that accepts the same language as M, its running time must actually be comparable to g of n, so that the simulation is halt.
I see.
Very clever, very cleverly designed, right? So I've constructed a machine which is almost like the most efficient machine for that language. Up to log n factor.
So about diagonalization then. So is the because we didn't construct like a matrix for this, but I guess we could have, right, if we had wanted to.
Yeah.
So the diagonalization aspect of this was essentially passing in the same Turing machine that accepts the same language.
So I guess there are two aspects to the diagonalization. One is that, and the second is the flipping the output.
Oh, sure. Okay.
So both of those together is that's the diagonalization.
Gotcha.
So I'm going to say this again. For this machine, maybe I should even write this down. M prime is like the most efficient machine, almost, for deciding LM. It's almost the most efficient machine, because if there was a much more efficient machine, then you get a contradiction. It's pretty amazing when you think about it. And again, the M double prime that was there was only there so that, because maybe f of, I should probably explain that as well. So what could happen is, why couldn't you just feed M prime in here? And that's because maybe M prime's description is so small that this inequality wouldn't hold when you use M prime. So you simply just sort of make it long enough by adding comments or adding extra states to ensure that this holds, because in the limit you know that this inequality holds.
Okay, so we could say something like, the actual representation of n is just is tiny. It could just be log of n or something. Right? And so therefore we have to add stuff just so this inequality still works out.
Yes, because your assumption is only that you had a limiting assumption.
Yeah.
You had a little o type assumption. So maybe the actual machine for this had 100 states. That's it. And so you don't know if this, for whatever f and g that you chose, whether f of 100 log of f of 100 is going to be less than g of 100. But you say, okay, just take that 100-state machine and keep adding extra states until at some point its description is so long that this is going to hold now. And then when that holds, then you can get your diagonalization to work out.
I see.
So that is, it's a technicality. The M prime is a technicality. And in hindsight, I feel that if instead your assumption was for all n, fn log fn was strictly less than g, and suppose you had this condition instead, then M prime would have been enough. Right? Because with M prime you would basically get the same inequalities. So I'm going to sort of write this out here. So M is the most efficient Turing machine for the language LM. Almost, right? Up to the simulation factor that you get with a log, it's essentially the most efficient Turing machine for the language.
Could I ask a question?
Yes, please.
A little tangent over here, but since here we define this language L of M, can we define more trivial languages in a sense that have to be simulated in this amount of time? that are less like involved in the sense.
You mean
like a problem or something that can be scalable to f of n and g of n?
So what you're saying is, can you come up with explicit problems as opposed to using diagonalization?
Yeah.
So that's a good question. And so, the thing is with, if f and g are arbitrary, it might be hard. But actually, it is known that if f and g are polynomials, like if you just wanted to say that d times, suppose you wanted to argue, I think that like for this, there's an explicit, like suppose you wanted to say d time n to the c is a strict subset of d time n to the c plus 1, something like that. Then I believe that there are, I don't know, I should be careful saying this when this is being recorded. I'm not entirely sure. I do think that there are certain like game type languages that can be defined which are more natural, which don't use diagonalization, where for specific settings of this form, like you can actually show some kind of separation.
Okay.
So I believe you can do this for like some specific settings where you can come up with, like what you're saying is, so another way that this is described is this is not a natural language. So by natural means ideally you want a language that doesn't reference Turing machines in code. That's sort of what you're saying, like some kind of graph problem.
Yeah.
So,
Yes.
So that's like saying, is there a natural language which demonstrates such a separation? Now, for arbitrary f and g, I think this would be hard to. This may not be possible because, but I think for specific, like when f and g are polynomials, I do believe that there is something.
Okay. Thank you.
Now, using this argument, and this is going to be one of the homeworks, and I think if you do this homework exercise, you will understand this proof a lot better. You can actually show that P is not equal to exp. This is a little more trickier because remember, P is an infinite union. This is an infinite union. So it's easy to just this exact same argument. Like you could say, okay, I'm going to just take, suppose g of n was 2 to the n, which I could do. And then I can apply this argument. I know that, d time n to the c is not in d time 2 to the n for all c. But this by itself does not imply p not equal to x because this is an infinite union. So you have to be careful, right? You can't take this does not imply that I could immediately just take the union. Right? Because this is an infinite union. So you cannot make this claim, but you can still perform the diagonalization. You have to think a little bit more about it. Essentially, because this is a countable union, you can kind of fold in a similar kind of argument with diagonalization. And so I'm going to probably give this as one of the homework problems. But this is a very important theorem. So P is not equal to exp. One can do this through diagonalization, and I'll give some hints in the homework. So now this gives us something quite remarkable, which the first time I saw this, it kind of blew my mind. We know that P is a subset of NP, and this is a subset of exp. But P is not equal to exp. So either, sorry, just a second. So, quite directly, the time hierarchy theorem tells us that so either P is not equal to NP or NP is not equal to exp. So what this tells us is, of course, this is what we've been looking for. What this tells us is, or what happens is, there are languages which are in exponential time that don't have verification strategies, right? That don't have a verifier in terms of NP. So SAT cannot solve things that are there in exponential time. So we have this or this. So it seems like we're so close, but to get a proof of either one of them, this is like the $1 million question. And indeed, you might think maybe there are like variants of diagonalization and some clever tricks one can do, and people have proven, and I'll talk about this later in the course, that actually that one has shown that there are whole classes of methods, proof techniques that cannot prove P not equal to NP. But my whole, the reason why I wanted to talk about the time hierarchy theorem was to show you this. So you know that P is not equal to NP or NP is not equal to EXP, sort of straight from this. So
why can't they both not be equal to each other?
Which is what we think, but we can at least prove this.
Okay.
We can prove this, but
it's not an XOR. It's like
no. It's you know. I should say that maybe there's no either, this or this. I shouldn't have said either. That was bad phrasing on my part. So we know that either P is not equal to NP or NP is not equal to EXP. You know, we think both. Or I should say we being complexity theorists.
That's a shame that we can't.
So with this, so we have P not equal to EXP. Therefore, we know that P is not equal to NP, or NP is not equal to EXP, both of which would be amazing to prove, or either of which would be amazing to prove. And so now it's time to start sort of a new chapter in our discussions, and let's talk about space complexity. So we're going to bring in another resource. And so to define space complexity, we will use more tapes. This is going to be convenient because we're going to discuss algorithms that actually use less space than linear. So there's going to be an input tape, which is read-only. And then there's going to be the work tape, which is the usual tape. You can also imagine an output tape where output gets written. We may or may not use output tapes. We might usually we'll think of languages where output tapes are not necessary, but I'll just sort of write that down. So you could imagine having an output tape, which is sort of the final result. Okay. So let's think of our Turing machine. And again, as I said, I'm not going to think of the output tape right now unless we really need it. So we have the input, and this is read-only. So the head can go back and forth and can read the input but cannot write anything there. And over here, we'll have the work tape, the workspace or the work tape. And this is where sort of all the action happens. This works as usual. So this is like a two-headed Turing machine. And again, we could have more tapes if we needed. We could have the output tape. And let's not get into that. The important thing is that the input is read-only. So now what I can do is I can define, let S be a function, be space constructible. Again, this is a technical condition that we don't necessarily need to get into. For now, if you didn't want to worry about this, just think of S as a well-behaved function. Logarithms, polynomials, the sort of nice functions that we use when we describe time and space complexity. So space S of n is the class of languages decided by Turing machines using at most C times Sn workspace. So we only measure the amount of space that is used for the workspace. We don't measure the input. And where C is, of course, C is a constant. This is some constant. Okay? Now, the reason why this becomes interesting, the notion of an input space, input tape and a work tape, is S of n can be less than n. I didn't put the exclamation mark there because I don't want you to think n factorial. The workspace could actually be less than the input itself. So we can actually think about space, the workspace, being so small that you can't even write the input on the workspace. But of course, you can read the input. And within this, now that we have P space, which is all polynomial space algorithms, we can have non-deterministic P space, where I can have the same definition except use non-deterministic Turing machines, right? Exactly in the same way. So I'll just say non-deterministic space, n to the c. This is P space and NP space. And then we have a language called L, which is very interesting. So L is space that's logarithmic. So it's actually very little space. It only has logarithmic space. And we have NL, which is non-deterministic space. So these are the languages that we are going to be discussing over the next maybe 3 or 4 weeks. And we'll see lots of beautiful results and surprising results about this, showing that we actually tend to know a lot more about space complexity and how it interacts with non-determinism and complementation rather than time complexity. Now you might say, why is the space log n? Why isn't it more than log n? And there's a very good reason for it. So you need, I'll say O of log n space just to write down the input length. Right? If you just wanted to write down what the length of the input was, you need log n space. And so in like less than log n space, it's hard to, one isn't able to do much in this standard model. That isn't to say that there aren't algorithms that use very little space. There is a whole class of algorithms that do things like constant space, but that's in a very different setting. It's hard to even decide like very simple languages. Or I should say it's not possible to decide very simple languages, because you can't even like look, the space is not even enough to write down the length of the input. Right, so it wouldn't even be able to keep track of, sort of it goes to the end, and how many steps has the head moved. And so these classes are going to be sort of the topic for the next couple of weeks. And so I'll end with that, and next week when you come, we'll be looking at P space and NP space more.